video, we're going to talk about how to do complex number operations. Complex numbers are numbers that have imaginary parts to the number. We have the real part and we have the imaginary part. So we need to know a little bit about what that I means. It's not a variable like x's and y's that we've had in other algebraic expressions. I actually means something. I is used to equal the square root of -1. If you remember in the past, we've never been able to take the square root of a negative number. And when we've been doing problems like the quadratic formula, we get stuck at the square root of -1. So when we use an imaginary number, I, to represent that -1, we can go farther and get a solution. So one thing to keep in mind as you're doing your operations is that I is always equal to the square root of -1. Therefore, if I take the square of both of these terms, I also know that anytime I come across an I squared, that equals -1 also. So this, if I take square of this and square of this, it'll cancel that square root and it equals -1. So these are the two principles that we're going to use when we're doing our operations. Other than that, we do treat the I like a variable. When we're using it to simplify expressions, we treat it like a variable. So let's look at a first example. When I look at this first example, I can tell that we're adding because of the plus sign here. So it would be very similar to what you would do if it was 3 plus 2x. We would treat it the same way. So when we're adding, if you remember, we only can combine like terms. And that's what we're going to do here. So I have a 3 and a 5. Those are just the real parts of my answer. So I can combine the 3 and the 5 by adding to get 8. Now I'm going to add the imaginary part. I have a 2i plus a -6i. So 2 plus a -6 is going to give me -4i. I cannot simplify this any farther, so that is my solution. So when you're adding, you just combine your like terms. Very similar to adding is subtracting. You again are combining like terms with one small adjustment. And if you notice this minus right here, we want to make sure and distribute it to everything in the parentheses first. That way we make sure that we are always subtracting. It helps cut down on errors if you do this first. So I'm going to distribute this negative to turn this into a -6 and a +2, because a negative times a negative will turn that into a positive. Now I can treat this like an addition problem. So I'm going to add my real parts up, 2 and -6, to combine to be -4. Not yet. -4. And then I'm going to combine the imaginary parts. I have a 7i and a +2i, which will combine to be 9i. Since there is no further simplification that I can do to this problem, I'm done at that point. So just remember that when you are adding or subtracting, we are combining like terms. The last thing we need to talk about is how to multiply when we have complex numbers. So we know that we are multiplying because we notice there is no operation between the parentheses. We know when no operation is given, that always implies multiplication. And just like when you would multiply a binomial times a binomial, we need to make sure and multiply everything in both parentheses. Some people say they FOIL it out, they do first, inner, outer, last. That's what I'm talking about here. Some of you use the box to multiply, whatever method works for you. So I'm going to multiply the 2 times the 2 to get 4. I'm going to multiply the 2 times the -5i to get -10i. I'm going to multiply the -4i times the 2 to get -8i. And last, I'm going to multiply -4i times -5i to get +20i squared, because it was I times I, in this case, to get I squared. So make sure if you're multiplying 2 terms times 2 terms, you're going to end up with 4 terms, just like we did when we were multiplying binomials before. Now we're going to simplify. There is nothing to combine the 4 with, so I'm just going to bring the 4 down. Notice I want to combine like terms out here. I have a -10i and a -8i. Since they are both i's, they are like terms and I can combine them. Those will combine to be a -18. plus 20I squared. Now, here is where our rule is going to come into play. We know that I squared is the same as negative 1. So we can simplify this right here to be negative 1. So instead of this I squared, it's really the same as multiplying it times negative 1. So I can simplify this one step further. 4 minus 18I, and this is 20 times negative 1, which is negative 20. Now you can probably see we can simplify it even one step further because I have more like terms here. I have a 4 and a negative 20 that are both just numbers. So I'm going to combine those to be negative 16 minus the 18I. Notice that unlike variables, we put our I at the end. That's just the way we write complex numbers. We generally put the real part of the answer first and the imaginary part second. So that's why you usually notice that the I is second. It would not necessarily be wrong to have negative 18I minus 16. Those really mean the same thing, but generally mathematicians like to write it with the I as the second term instead of the first. That's just what you typically see. All right, let's do one last example. I wanted to show you where we see imaginary solutions come up a lot. When we use the quadratic formula, we come across negative square rooted numbers, and that's when the I becomes invaluable. So I wanted to show you what that would look like when you come across it. So we know the quadratic formula, x equals negative b plus or minus square root b squared minus 4ac all over 2a. And if you remember what we've practiced before, we plug in the a, the b, and the c. So if I plug it in, I plug in my b, which is negative 8. I plug in my b again, minus 4. Plug in the a, which is implied to be a 1 because there's nothing there. Plug in the c, all over 2a again is 1. Now I'm going to simplify this down. Notice I have a negative 8, so that is going to turn into a positive 8. If I have 8 squared, that's 64. Right here I have 4 times 27, which is 108. And 2 times 1 is 2. All right, 64 minus 108 is negative 44 over 2. So now you know that your next step is to reduce this radical. In the past, we've always said you can never take the square root of a negative number because it's non-real answers. And it's true, it's not a real solution. But we now can simplify it further because we have the use of imaginary numbers. So anytime we have a negative, we can take it out as an I. Let me show you how that looks. First, think about if I was just going to reduce 44. Remember that we look for a perfect square that divides into 44. Well, I know, I'm going to copy this up here so I have a little bit more space. I know that 4 goes into 44 11 times. So I can break this down to be 4 times 11 times negative 1. I'm going to put them in parentheses. I think that looks a little better. So negative 44 is the same as 4 times 11 times negative 1. I'm just breaking it down first so you can see what I'm going to do. Now, if I take the square root of 4, that's 2. If I take the square root of 11, I'm going to get a really long decimal place. So I'm going to leave that inside the radical. We don't want any decimal answers. We're just trying to do it in reduced radical format. So if it gives a long decimal, we're going to leave it in there. There's no perfect square that would go into 11, so that's as far as that number can be reduced. The square root of negative 1 is I. So now I have reduced this to be 2i square root 11 over 2. Now I have one step that I can reduce this a little bit farther. If I notice that I can divide the denominator into both of the numbers in the numerator, we're going to ignore this square root, but both of these, then I can reduce it one step further. So my final answer is 8, oops, I didn't divide it. 2 goes in 8 4 times, 2 goes into 2 one time, just leaving the I, square root of 11. So my solutions for this quadratic, I have 4 plus I square root of 11, and I have 4 minus I square root of 11. That's my two solutions for this quadratic, and that's where imaginary numbers come into play. So that's it for complex number and operations. Engineers use this a lot. It's used in the real world for electrical engineering and that kind of stuff, so it's really interesting to study imaginary numbers because they come into the real world too, which is surprising because it's imaginary numbers.